David Sibeck, it's an honor to have you here today. Your career has spanned decades of groundbreaking research in space weather, magnetospheric physics, and leadership in major NASA and international programs. And to begin, could you briefly describe or share how your journey in space science started and what inspired you to dedicate your career to understand Earth's interaction with the solar wind?
Yes, bom dia, Claudia. Uh, my journey began a long time ago, 50 years ago this month, when I went to university at UCLA in Los Angeles. I had no intention whatsoever, no intention to go into space physics because I didn't know anything about space physics or that it existed. My intention was to become a meteorologist and to predict the weather and to study that. And so I enrolled in meteorology and everything went fine. And at the end of my first class in meteorology, they said, "You're going to get an A. You're going to get the best grade. And that means we're going to offer you a job." I said, "Oh, that's great. I'm going to learn how to forecast the weather." And they said, "No, you're going to work with people who study space weather and space." I said, "Oh, I don't know anything about that at all." They said, "That's okay." This was so long ago that there were not computers and there were not many computers, and so my job was to take a pencil and a piece of paper and make plots by hand, dot 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 dot, and connect them by line and about the Earth's magnetic field. That went well, and they asked me to take courses in that subject. They asked me to stay on at UCLA to go to graduate school, and again, by great fortune, not by planning, not by design, NASA had decided to move one of its spacecraft from upstream in the solar wind to downstream in the magnetotail for the first time. And so I would be able to look at the first observations of the distant Earth's magnetic field and do my thesis work on that. And I was sent to JPL in California, not so far from UCLA. And I met a completely different group of people, different scientists, and I sat with them Monday to Friday. I came back to UCLA and worked on Saturday, Sunday to complete my thesis. Again, by wonderful fortune, just as I was finishing my doctor's degree, there was a visitor from APL. APL is a laboratory here in Maryland, Applied Physics Laboratory, and they had a new spacecraft. And they said, "Would you like to come and be a postdoc with us?" Having worked with spacecraft data, having studied the magnetopause, I said, yes, I would. And I came and worked at APL for a long time. Now, the contacts I had made, and contacts are really important in our subject. It's the people you know can help you get things done. The people I had met at JPL moved to other places, including moved to NASA Goddard Space Flight Center, but they remembered me. They remembered me when I was a student. And they said, if you ever want to come to Goddard, we can make it happen. You can come and work at NASA. And at a certain time, I thought, I want to learn about missions. I enjoy doing science, but I want to plan missions. I want to have my own mission. I want to organize groups of people. And so I said, yes, I want to come to Goddard and I want to work on missions like Themis, missions like Van Allen probes. And the great advantage of working on those missions is that I learned how to formulate, how to design, how to plan a mission, and then I could try to plan one myself. And so since then, and most recently, we've been trying to make plans for our own spacecraft mission here to study the Earth's magnetosphere and its magnetic field. So that's kind of my chronology to reach this point here at Goddard.
Starts as a meteorologist. I know that the name is different in our country, but are you meteorologist, physicist, or something else?
I am a meteorologist by training, but during the time when I was at UCLA, they somehow became embarrassed that that was an old-fashioned term, that it sounded like something from history. And so the department name changed to atmospheric sciences. And that sounds much more formal and much more advanced. So meteorologists became atmospheric sciences. But I still think by training, a meteorologist.
So, looking back at your time with missions such as EMPTY that you mentioned,
Yeah.
Themis, Artemis, and Van Allen probes, tell me more about that.
Okay. The first mission that I studied was as a graduate student when I was at UCLA, and I was sent to JPL. And JPL was one of 3 places in the United States that could build magnetometers. And they had built the magnetometer for the IC-3 spacecraft, which was serving as a solar wind monitor at L1. But a comet was coming, and it was called Comet Giacobini-Zinner. And there was a plan that if we could move that spacecraft from the solar wind monitor, we could make it catch the comet and see what a comet is like. And it was a very complicated path that it had to follow. So it went into the Earth's magnetotail and all around the Earth, and then off it went to the comet. So that gave an opportunity to study the Earth's magnetotail with IC3. That was the first data set that I looked at. When I came to APL, the AMPTY mission had launched. And this was an international mission with with British and German and United States scientists. And it had 2 purposes. Purpose number 1, they were going to release barium or lithium clouds in the solar wind and see if they could get into the magnetosphere. They didn't. But it also could measure what was naturally occurring there. So it measured the magnetopause, the radiation belts, the composition. The United States spacecraft was called Charge Composition Explorer. And so it measured what was in the ring current and the radiation belts, the charged energetic particles deep inside the Earth's magnetosphere. After that, we had the ISTP program, which was an international program. I wasn't a active member of any team, but NASA had changed its policy. All of the data from all of the spacecraft would be publicly available. Anyone could look at anything. Oh, what a dream that was. I could look at magnetic field or plasma or particles from all of those spacecraft, stack them up, see how they related to each other, test theories on that. And so I worked on that for a while. When I came to Goddard, the Themis mission was under consideration for launch. It had not been chosen. And shortly after I came to Goddard, NASA announced we're going to launch the 5 spacecraft Themis mission. They're going to each go into their special orbit, synchronized to be measuring at the same time. And then, according to NASA policy, there should be a NASA scientist who is responsible for each mission. And I was the only person associated with this mission who worked at NASA. So it must be me. I must be the person at NASA who would take care of it. And oh, that was a joy. And it is a joy until today, because that mission launched in 2007. It's still flying. All of the spacecraft are still working. 2 of them have gone off to the moon, even more exciting. 3 of them are in the Earth's magnetosphere. It's great. And then the final mission after that I worked on was Van Allen probes. And that was also a pleasure. It was absolutely fascinating to be there from the very beginning, where they said, well, how many spacecraft should there be? What orbit should they go to? What instruments should they carry? How will we make this opportunity available for people to propose? Which ones will win? There were many different competing ideas on which spacecraft to launch. Many ideas about which way the spacecraft should point. How fast should they move? How fast should they spin? As a scientist, it was fascinating to engage with the engineers and pose questions and answers. Well, how would we do that? What is the best choice for this? So those are the missions that I worked with.
Okay, so would you explain better what does Themis mission means? What and also the Van Allen probes
Okay.
and what discoveries
Yeah.
do you
So
personally
when
consider
it
the most transformative for our understanding and according to these missions?
I would be delighted to explain the Themis mission. The Themis mission, first of all, it came out of very inspiring ideas by the principal investigator, Vasilis Angelopoulos. And again, I want to point out the importance of meeting people, getting to know people, because in our field, it's connections that matter. During the course of my studies during ISTP, I had found it was fascinating and enjoyable to visit the University of California at Berkeley. I visited Taifan, a wonderful person, a great scientist. But while I was there, I met and talked to Vasilis Angelopoulos over and over again. And so when he wanted to write his proposal for the 5 spacecraft Themis mission, he wanted to study substorms, but he knew that the spacecraft would go to other places. They would go to the radiation belts. They would go to the magnetopause. They would go to the bow shock. He is a substorm specialist. So he turned to me and he said, would you please write a section of the proposal that tells what they will do when they go to the day side, to the magnetopause, to the bow shock, to the sheath? I was delighted to do that. If we win, you will be part of the winning team. Great. So the Themis spacecraft mission is a 5 spacecraft mission. Each of the spacecraft measures the Earth's magnetic field, measures energetic particles, measures plasmas, measures magnetic field waves, measures the electric field. So comprehensively instrumented spacecraft. And unique for NASA missions, this mission had an intrinsic demand, a requirement to put an array of ground observatories across Alaska and Canada with cameras looking up every night into the sky for aurora and magnetometers on the ground, same kind of magnetometers that are throughout Brazil, measuring variations in electrical currents in space. Why is that? Because even 5 spacecraft is very few given how big space is. But we can map out all the magnetic field lines that go to space by putting magnetometers and auroral cameras across North America. So the purpose, the main purpose, every NASA mission has to have a main purpose. And when the mission ends, somebody has to verify it did achieve that purpose. The main purpose of the Themis mission was to decide what causes geomagnetic substorms. Some people said it is due to a current instability, some kind of wave. Other people said magnetic reconnection in the magnetotail. And right from the start of the mission, it became clear that it's magnetic reconnection. The spacecraft were lined up to see where reconnection began, where the fast flows occurred, where the magnetic field changes, and time them to see how they propagate. So that was settled early on. The mission achieved its objective, but such a successful mission, it has helped people studying everything. It helps people who study radiation belts like yourself, people like me who study dayside, people who want to study auroral phenomena, and continues until this time. So that the big discovery and the big success of Themis was discovering when and where substorms begin, and especially why. They begin with magnetic reconnection. Magnetic field lines come together, snap like that, and plasma jets off like that. And some of that plasma goes into the radiation belt. Some of it goes down magnetic field lines and makes aurora.
That's great, but would you explain me and for my audience all the relationship between the sun and the magnetosphere, how everything happens, and why, and step by step, how
Okay.
all this
So
process happen?
I think I would like to explain to you how a geomagnetic storm occurs. And then after that, I'll explain what this other phenomenon, substorm, that Themis measures. But geomagnetic storms are the big ones. They occur maybe once or twice per month, especially at solar maximum. They occur when there is an explosion on the sun. and a coronal mass ejection, a big blob of plasma and magnetic field is hurtled off, sent into space. It could go in some other direction and never come to Earth. Then we just observe it, we study it scientifically, and we say, that's interesting. But if it comes straight at us, and we have spacecraft to look and see if it's coming straight at us, we can predict it 2 or 3 days in advance. We can measure it as it's coming by this L1 libration point, 200,000 kilometers upstream from Earth. And if it brings especially strong, dense plasma and especially strong magnetic fields, in particular magnetic fields that point southward, as opposed to the Earth's magnetic field that points northward, perfect for reconnection, that's going to put a lot of energy into the Earth's magnetic field. Energy, particles, mass, and the Earth's magnetic field will capture that energy. And interestingly, it captures it, and it captures it on the night side of the Earth. And it stores it on the night side of the Earth until it can't store it anymore. And it doesn't release it gradually. It releases it dramatically and suddenly and pushes that energy, that hot plasma, those energetic particles earthward. It pushes them into the radiation belts. It pushes them down magnetic field lines to the north and south poles of the Earth to make aurora. It builds up the radiation belts. It builds up the ring current. And this is a current circling the Earth at big disturbances in the magnetic field all over the Earth, disrupts communication. Danger for satellites in the vicinity of Earth, could disrupt their electrical circuits. And that's a geomagnetic storm. And then the smaller phenomena, the substorm, are little incremental parts of it that build up to that, little smaller. So storms and substorms are the big space weather phenomena in the Earth's magnetosphere. They're hazardous to spacecraft, to communications, to astronauts in our vicinity.
I'm suspicious to say anything about the Van Allen probe's mission. One of the most important and significant mission for me, for Brazil, for our area, for the Van Allen radiation also. And yes, I'm so proud to be part of this mission and to contribute to our researchers in this area. And it still continue.
Yes, you are an active participant in the analysis of Van Allen probes. So Van Allen probes was a different kind of mission than Themis. In the Themis mission, there was an open competition, and whoever wrote the best proposal would win the money and build the spacecraft and run the mission. Van Allen probes, there was assembled a group of expert scientists. What is the most important problem that we need to solve right now? And the answer that they gave is we need to understand the space environment in the Van Allen radiation belts. We need to understand geomagnetic storms. And so then they worked for, well, how would we do that? And at the beginning, they were so optimistic about money. We'll have 20 spacecraft and put them everywhere. In the end, there were 2 spacecraft, but 2 spacecraft is good, because 2 spacecraft, if you just have 1 spacecraft, you don't know if a change is because something changed in time or in space. But if you have 2 spacecraft, you can see if it's still there or if it's moving, whatever it is. So the objective of the Van Allen probes was to understand the Earth's radiation belts and its ring current to a sufficient degree that we could improve space weather forecasting models for this hazardous region. And another aspect was to provide real-time data. And I believe you helped in making that happen. You personally helped to provide real-time data to space weather forecasters, because if you know what's happening, it can help you protect your instrument. For example, there are astrophysics missions that should turn off when there's a storm or dangerous radiation. They would like to have a warning. It's getting bad, turn yourself off. So the mission launched with a big array of particle instruments, from very cold, very low energies to very high energies. That's important because the high energy ones come from somewhere. They come from low energy ones that got energy. How do you energize a particle? You need an electric field, so it needs to measure electric fields too. What happens in the Earth's vicinity? Very much controlled by the magnetic field. So the spacecraft needed a magnetic field. So two identical spacecraft measuring particles, electric and magnetic fields, going in and out of the radiation belts. And as I mentioned earlier, it was extremely fascinating to see the planning that went into this, because before NASA announced we're building this spacecraft, I think very, very carefully, we are sending two spacecraft to the most hazardous place in Earth's vicinity, high radiation. Everyone else wants to avoid that place, to stay away from there. And you are purposely putting them into a place where they're going to have terrible, dangerous radiation. How are you going to protect the instruments? How are you going to protect the spacecraft in there? So there were lots of calculations. How thick do the walls of the spacecraft have to be? How long, what will you cover that instrument with? How long can it operate before it will have problems? All of those sort of questions need to be answered. Questions like, which way should they point? Should the spacecraft axis point at the sun and spin like this? Or should the axis point like this and it spins like that? All of these decisions have big consequences for the science you can do, for how long the spacecraft will last, for how many instruments you need. And you have to go back and forth. They say, well, if we do that, it's cheaper. But these people will complain, and then vice versa, until some design is open. And then proposals were received, and there was a difficulty to decide which proposals, which teams do you want, how will they work together. And the hard thing was telling some people, we like part of what you propose, but we don't like that part. No, you should do all of it. But in the end, it was all settled and done. And again, NASA had a policy of open data, so everyone could participate. And lots of people at INPE have worked on Van Allen probes data since then. It's been a good experience, a wonderful international cooperation between our two countries. And that mission has been successful too. And earlier in this conversation, you asked me, what is the most important finding from the mission? Probably the single most important finding from the Van Allen probe's mission was to decide where and how and by how much do particles get energized to dangerous energies. And I think the consensus is it is done by plasma waves generated in the ring current that up the energy until the particles are very high. Alternatives were they're just pushed in, or by big global waves. No, it's by local waves in certain regions that raise their energies. But there are a lot of waves and there are a lot of things can happen. But that's probably the most important discovery.
And you have collaborated with programs in Russia, the Czech Republic, and Slovakia, and received recognition from Charles University in Prague. How important is international collaboration for advancing in space science?
Yeah. So personally, I think one of the most enjoyable aspects of our field, space science, is the international collaboration. It's essential, but it's also extremely enjoyable. And it's essential because when you think about it, space is absolutely enormous. No single spacecraft can solve the problems. No single country can solve the problems. Agreements between people and countries are essential. Some country is good at ground-based observations. Some country can build an instrument to measure particles. Another one can build magnetometers. International cooperation is fundamental to our field. It's been my greatest pleasure to work with scientists around the world throughout my career. And I think by doing so, we learn so much by hearing other people's viewpoints and seeing their contribution. There's something for everyone to do in our field, for instrument builders, for theorists, for modelers, for data analysis. And each person and each country has their natural specialty. So it's different to other research fields. Other research fields are not like that. Our field, international cooperation, is excellent. And you for example, are a good proponent. You have made friends from around the world and cooperated with people in countries you could never dream of when you entered this field. And that, you are a good example of that.
I totally agree with you. Yeah, you also helped set up NASA Living with Stars program, and which is a central program to space weather research. And how has the program evolved, and what impacts what has it had on our ability to forecast and mitigate space weather effects? Also, how this study define the U.S.'s force space weather needs, and how they can use it to protect assets
Mhm.
in space
So
on the ground.
the findings from the Living with a Star mission have been published in papers, but how do we know when we've really done something well? How do we know when it's useful? How do we know when it's practical? If we can predict something successfully, then it means we understood it. And so we should incorporate these findings in models. And there are now several models for how the Earth's magnetosphere operates, how particles are energized in the radiation belts. Some of those models run here at Goddard, some run at other places like Los Alamos or University of Michigan. The results from Van Allen probes are put into those models. Where and when should plasma waves occur? Where and when should magnetospheric phenomena make plasma waves? Where and when should those waves energize particles? And so we have much more accurate models now, after the launch of Van Allen probes, after those results have been obtained, after the models have been improved, that can run either in retrospective to understand things that happened in the past or in real time. So here at Goddard, we have models running in real time to predict conditions in the magnetosphere based on solar wind observations. We make forecasts. In our country, NOAA is the agency, the National Oceanographic and Atmospheric Administration is tasked with that. But there's a close cooperation with scientists and with NASA to transfer that information into their models. And the Air Force also is very interested. There are programs to cooperate. The Air Force needs to know about space weather. For example, if we're launching NASA missions, we want to make sure to launch them at a time and on a day when they'll be safe as they go out through the Earth's radiation belts. Yeah.
And recently, you've been leading efforts to prototype a wide field of view soft X-ray imager. Could you explain how this technology works and what new perspective it would bring to
With
solar
pleasure.
and
You may
magnetosphere
have
studies?
difficulty getting me to stop talking
You can
about
use all time you have.
if you ask a question like that. Right. But one of the wonderful things about working at NASA Goddard Space Flight Center is it's a very big organization, and there are many people doing many different things. And my good friend, my colleague Michael Collier, introduced me to astrophysicists. And these astrophysicists said, when we look in certain directions in the sky, we get a fuzzy picture and we see things that are obstructing our view of the stars. It doesn't happen every day. It just happens on some days and in some look directions. And after a lot of thinking about it, we realized that that was happening when we look through the magnetosphere, when we look through the magnetosheath. So there's something in the way. And people at first couldn't understand what could that be, because X-rays, you usually think, come from something very hot like the sun. But there's nothing very, very hot in the Earth's, not like the sun in the Earth's magnetosphere. And what it turned out to be was line emissions. When a high charge state ion, for example, carbon 6 plus or oxygen 8 plus, captures an electron, it decays in energy and it sends off X-rays, but only at one frequency, only at one line, only at one wavelength. And this is what's happening when solar wind ions meet Earth's atmosphere. They hit each other, they exchange electrons, and they produce X-rays. line emission X-rays, single wavelengths. So where does this happen? It happens in the Earth's magnetosheath, and it happens in the cusps. And what you want to see this is a very different instrument than astrophysicists usually use. Astrophysicists usually have a big telescope like this, and they're looking at a single star like that, trying to understand it. But we are magnetospheric physicists, and the magnetosphere is this big target. We want to back away from the magnetosphere, and we want to see the whole picture. And so the kind of instrument we want to use is very different than what the astrophysicists normally use. They know about this instrument, but they don't use it very much, and they don't have much use for it. It's called a lobster eye telescope. And in this lobster eye telescope, it takes a big picture of the sky where the X-rays come in and they bounce and they come down to a detector plane like this, but from a wide field of view. So what is the advantage and disadvantage of this instrument? It can see a lot all at once, but it's not nearly as strong as the powerful astrophysics telescopes that just look at one star at a time. So we have been very actively engaged in developing this kind of instrument. We have flown it several times on rocket flights. It flew on a CubeSat, but unfortunately there was no communication with the CubeSat, so we didn't get any results. But the rocket flights worked, and we attempt to propose it for big NASA missions. In recent years, NASA has launched in situ missions like Themis. They measure at a point. Van Allen probes at a point. MMS, they measure at a point. These can tell us the microphysics or what's happening right there. But if we back off and put cameras, we can take pictures of the Earth's magnetosphere in soft X-rays, of the auroral oval in far ultraviolet. We can take pictures of the ring current in energetic neutral atoms and get a global picture. So our position, our argument is, now that we understand the microphysics, what's happening locally, let's see the global picture, how it's all put together with a comprehensive imaging mission.
Yeah. And what directions excite you the most in current research, whether in simulations, force-shock microphysics, magnetospheric process, or geomagnetic pulsations, or AI? I don't know.
Okay. So I'm actually going to be speaking to INPE in only a couple of weeks about exactly this subject, and so it's on my mind. I personally am a dayside science person, and so I'm interested in everything. We have a wonderful group here. We have a student coming from Brazil very soon who wants to study the radiation belts here, and we will work on that. But me personally, I am interested in the structure and transients in the solar wind that are coming in and driving the magnetosphere. I'm interested in the foreshock, where some of the solar wind bounces back and generates turbulence and waves. I'm right at this minute writing a paper about the magnetosheath response to a big change in solar wind pressure. I love the magnetopause and transients on the magnetopause and reconnection on the magnetopause. And then, in our field, there's this kind of teleconnection. Things in one place are connected by magnetic fields to someplace far away. That's one of the unique features of heliophysics, is something happens over here and it has a consequence over here. So I'm very interested in what's happening down at the footprints of magnetic field lines at high latitudes in Greenland, in Canada, in Iceland, and in Scandinavia. And years ago, when I first visited INPE and worked with Trivedi, we then went down to the equatorial regions, and we saw signatures in Brazil of things that were at Greenland, that were at the magnetopause, that were in the solar wind. So I guess I am interested in that intricate series of connections from the solar wind all the way down, and understanding what's happening at each step all along the way.
Are some region
To say
included
what?
in this talking about the footprints or how the summer region are correlated with this process that you are mentioning?
Oh, SEMA. Yes, South Atlantic magnetic anomaly. Yes, I mean, we absolutely want to understand when and where and why and how much precipitation occurs in the South Atlantic magnetic anomaly, we should probably say the Brazilian magnetic anomaly, right? Because it's moved over Brazil now, so maybe it's time to change that name. Yes, that's at the very inner edge of everything we do, all the way down, and an important place for spacecraft operations, right? Those that go through it are subject to radiation.
And how about AI? How AI are included in all this
Okay,
subject
so
inside
that's
this?
a major area here. I see big initiatives occurring here. We just had a seminar last week. What do you do when you have thousands and thousands of millions of images of the sun that no human being can look through? I mean, my entire training and the way I trained students was let's make pictures and look through them one by one. But what if you have millions and you can't do that? It'll have to be AI, and they're getting just superb things in AI along the lines of what happens just before something erupts on the sun. As human beings, you and I cannot look through millions of such events, but AI can, and it can decide this is what's typically there, and then we can go test it on some new data set. So that the future for that is very bright. And I would encourage early career scientists to learn about AI.
But never forget the science, don't you?
But never, no, it shouldn't just be computers. We want to achieve scientific understanding. But that's the joy of our subject. I was thinking, what is it that gives me happiness? The happiness is there's several things. Seeing something for the first time, that's a pleasure, but even more is understanding it for the first time. That is the feeling when you say, I know what's happening, there's a great pleasure in having that feeling.
Um, you've mentored many productive postdoctoral researchers throughout your career.
Yeah.
What do you find most rewarding about guiding the next generation of scientists?
Okay,
What do
so
you hope your
there is a
scientific legacy will be?
philosophy that some people call pay it forward. Pay it forward means as I have been trained, so I will help other people. And I was so fortunate to have a good advisor for my PhD thesis, a very kind, a very patient, a very knowledgeable person, George Sisko at UCLA. And he installed in me a way of behavior that I would like to see other people have also. A patient way, a non argumentative way, a cooperative way to find the best in what other people are doing, to work together. So when I have postdocs here and sometimes graduate students here, we are looking for ways to introduce them to as many people as possible, to find interesting research problems, to question not just new things, but question old things. Is it really correct what's written in the textbook? Is it really right? Can you be sure that that's correct? Do you see something different? Open your eyes to look at the data or run the model to do something new, to find something different. And I would say one of the happiest things for me is when I see the people I have mentored go out and achieve success and work with each other without any help from me. That means they've become independent and they are going on to do interesting and good things. And it's some of them are university professors, some of them are researchers, some of them are doing things like you're doing, which are I mean, you are attracting people to science. You are encouraging people to think on their own, get involved, do something. And that is a joy to see that. And that's gives me a lot of pleasure to do that.
Oh, David, it's so good to hear from you all of this. If you're following your mentor instructions, you are successfully reaching out all of this because you know that you have been doing all of this for me and for all the students that have been working with you. I can probably include all of them, and me, Renia, Ankush, Vitor, also Marcos, and now Karen that will be with you, and so on. So many students that have been working with you, you are inspiring, you are like all of this that you mentioned from your mentor, you
Yeah,
have been doing
Ankush,
this for
wonderful
us.
people,
Thank
success,
you.
and others here. Well, you're kind, and I think that's what I wish my legacy to be. I wish that there's a group of people who are happy, enjoying their work, doing good work, and working together and staying in contact, as you have stayed in contact with the people you met. Yeah,
Sim, yes, yes, yes. I have been in contact with people around
man.
the world. So let's do something a little outbreaking. To start on a little note, what is
Oh,
one of
this.
your favorite movie? Maybe even space related one? Do you have one?
Oh, that's too hard. I love movies. I love foreign movies. But what is my
Okay.
favorite movie?
Don't worry, don't worry.
I'm gonna have to think about that. You come back to that one later and ask me that again. I have a program now of watching one old Russian movie per week, but those are for curiosity. I'm not sure I would say that any is my favorite, but I'm fascinated by them. Um, I'm trying to. I unfortunately cannot think of a favorite Brazilian movie, although I've seen Brazilian movies. Well, when I used to come to when I first began coming to INPE, well, I want to tell you about a positive experience. And when I was getting ready to come to INPE for the first time, I used to go to the fall AGU, which was always in San Francisco, and I would ride the public transportation there. And just for any time I had free time, I was going to look in a learn Portuguese book. And so I had that in my hand. And so I was riding on the bus, and somebody saw that and said, "Oh, are you learning Portuguese?" And I said, "Yes, I am. I'm going to be going to Brazil. I'm going to be working with scientists in Brazil soon. So I'm starting to learn some Portuguese." I said, "You are going to have the most wonderful experience in your life. The Brazilian people are the friendliest, kindest, nicest people that you will ever meet. And you have made the right decision." Oh, I was so happy to hear that. And you know what? It was true. It was absolutely true. Everyone in Brazil is, oh, it's wonderful. It was good.
People from Brazil also say that NASA research are the best in the world, and you all your job and all your work are like the most the powerful in the world. How do you say? Are you the best in the world? NASA is the best in the world.
No, I don't think I'm the best in the world, but I will have to say, as a certainly as children in the United States, we thought NASA was wonderful because when I grew up, NASA was preparing to launch to the moon, and I still have the newspaper from when I was 10 years old that the headlines, "A man walks on the moon." I kept that ever since then. Uh, so the ability to succeed, to go to faraway places, to solve problems, to walk on the moon, to send satellites to other planets, it captures people's imagination. And all of that attracts people who are dynamic and energetic and want to get things done. And so NASA maintains a high reputation. Oh, and I would say the United States government takes opinion polls on what is it like to work in this place. And NASA consistently scores the maximum score. I think our management tries to make this an enjoyable place to work, tries to, and I think it's a place where your ideas for change or to do something new are readily accepted. That if you come in with a good idea, you can do it, and you can do it, and people will help you do it. They want you to try to do it. It's also, I want to say, at least until recently, a place which made special efforts to encourage women and minorities to enter science. And it's just a very good feeling to see a place where everyone is welcome, and diversity and some kind of encouragement to try. It's really special.
I totally agree with you. Yes, for sure. NASA is one of the best places in the
Yeah.
world to work. I felt this when I was there. And the best thing in work at NASA is that you can go to NASA and find people from all around the
Yeah,
world. That
it's a
is
joy. It is a
interesting.
joy to come in, and they've all had. So I want to say one other thing about our field. People, very few people have come into space physics from the beginning saying, I want to do space physics. They have come in from different countries with different backgrounds. Some are very good at mathematics, some are good at data analysis, some of them are theoretical. You meet such an enormous diverse group of people. It's very inspiring. If you can find people who know the answer to almost any question.
One of the biggest questions that my followers also do to me is the man in the moon. Is it true? Would you please explain me? The man in the moon is true?
So well, there is a, if you look at the moon, you can see it there. And yes, NASA has landed on the moon. Moon rocks have been returned from the moon. We've landed space. We continue to send spacecraft to the moon. So I think you can come to the Smithsonian Museum and see some of these moon rocks. So yes, it's real. It's not a hoax. It was a difficult thing, but and now we go back to the moon. At least we try, and from then onward to Mars. But no, it's not an easy thing to do.
Okay, so if you have the chance to travel, would you choose the moon, Mars, or the International Space Stations, and why?
Well, if someone off, I think the international. Well, I could, if I went to the International Space Station, I would probably revert back to my meteorology training and want to take pictures of clouds and fronts. And I was fascinated by weather when I was young. But if I wanted more excitement, I think I would rather go to the moon. And what I would like on the moon, here's my special plan. I would like a moon rover with motorized moon rover, and I'm going to put a magnetometer on it, and I'm going to drive around looking for magnetic field variations and particles coming down, and drive all around the surface of the moon and map out the lunar surface. That will be my plan there. Now Mars is a bit tougher because it's going to take a long time to get there and a long time to come back. Assuming I'm coming back, I hope I'm coming back. So I maybe will stick with the moon. I'd like to come back home after a while.
And don't have fruits and nature.
Yes, yes. I love fruit that everybody who works with. Right now, on the table in front of me, you cannot see it, is a large mountain of our North American version of Achamoya. It's all my gardens. There's maybe 30 of them on the table over now, and I'm going to attempt to give them away today.
So, beyond science, what's a personal dream you still hope to accomplish?
What do I hope to accomplish? My primary goal right now is to organize things well for the people around me, that they can continue to carry on the work that we have started. One of those activities is winning a spacecraft proposal of our own. And the topic we are working on most at this moment is, if we go back to the moon, can we send our imager to the moon, to the surface, and look back at the Earth? So that's a very feasible thing to do. The moon is a good place, but as you know, one side of the moon always looks at the Earth. So this instrument doesn't need to spin. If you just put it and point it, it will look like that. So we would love to do that. So just yesterday afternoon, we had a big meeting here at Goddard of our team, and we drew up a chart of different instruments and different places that we would like to put them. And so as you know, we haven't talked about it, but NASA's in a kind of turmoil now. Many things are changing in our country, but we could be pessimistic, but we could also be optimistic. And like you, I'm an optimist. And so what is that? What it means is, let's prepare options. What can we do? What will we do? Expensive ones, cheap ones, distant ones, close ones. And let's go to our managers, our supervisors, and show them these are things that we're thinking about, which is interesting to you. Whichever one you can do, from very small to very large. And because we are not people who just want to sit here, we want to do something, and we want to succeed. So we will, right now, our big activity is finding some path forward in this very turbulent time. And the way we do it is not to just say we only do this, no, we do many things, and whichever one you can support, we'll do it.
Yeah, maybe you have better mission than before. Yeah. So, new opportunities.
That's right. We'll find some path forward, and in any case, at least we know we tried. We have to try. You cannot succeed if you don't try.
So, finally, what message would you like to share with students and young researchers worldwide, especially in countries like Brazil that are building capacity in space science and space weather research?
Okay, so my message for students and early career people is, dream big. You can do it. Don't be shy. Oh, I was a shy person when I was young. I think you realize I'm not such a shy person anymore. Not anymore. But go and talk to people. Visit INPE. Discuss with people there what they're doing. Ask them who's doing what. Find out. Get yourself involved. Volunteer. So you can't know what a scientist's life is like unless you meet scientists. Go and talk to them, meet them, find out, ask them their plans. Don't be shy. Engage them. Tell them your plans too. I'd love to hear people who have a dream or some plan. And as a good scientist, I want to help them achieve that. So be daring, dream big, go forward are my advice to early career people.
And how people can find you? Is there any email or website where they can find you, David?
Oh, easy. Anyone can Google my name. I'm on the internet, and I have had correspondence with students in Brazil, students who wanted to get into space physics research, and I will be happy and I will respond to people who write me. I will point them in the right direction. And, in the past, our country has had programs where students from Brazil and from other countries were invited to come and spend a summer at NASA. Let's hope we have those in future. And by students, I mean even high school or undergraduate students. It is possible. It is possible.
Was an internship at Goddard, you know.
Yeah, to do that.
So, David, I had the privilege of being your student during my time at Goddard, and I want to sincerely thank you for the inspiration and support you provide. Your work has a profound impact not only in the scientific community but also on students in Brazil, where your dedication continues to motivate us to pursue space science with passion and commitment. Thank you so much.
Thank you. Thank you for the interview. It's been a pleasure working with you. It's a pleasure talking with you. Yes, it is my dream to come back to Brazil, and not just for a brief stay, but for longer work at your institution. I have had already several conversations about that. And so we mark that down on our calendars for future activity. And for all your listeners in Brazil, I look forward to meeting and talking with them too. It's a
I hope you
wonderful thing.
can be here in person so we can talk together in my podcast. And thank
Yeah.
you so much. Bye bye.
Yeah.
See you.